Hi, I want to talk about the energy that we see for objects in their orbit. Now, objects that are in orbit have two types of energy. Gravitational potential energy, due to the force of gravity being a conservative force, and kinetic energy, because an orbit is an object in motion. Well, for a change in potential energy, it's going to be minus the work done by a conservative force. Well, our conservative force is the force of gravity. So what we could imagine doing is take an object infinitely far away and bring it to the location of its orbit around that object. Well, the force of gravity is the universal gravity constant times the mass of our object that's in orbit times the mass of the object being orbited divided by the radius of the orbit squared. And our path would just be along some change in radius, so our integral will give us a potential energy of minus the universal gravity constant times the mass of our object in orbit times the mass of the object being orbited divided by the radius of the orbit. Now for kinetic energy is 1/2 times the mass times the speed of an object squared. But the way we worked out Kepler's law, we applied the idea of centripetal force. The centripetal force equation tells us that the mass times the centripetal acceleration, the speed squared divided by the radius of our circle, is our force. The gravity constant times the mass of our object times the mass of the object being orbited divided by the radius of the orbit squared. Well, mv squared is just the magnitude of the potential energy. So that means that the kinetic energy of an object in orbit is 1/2 the magnitude of the potential energy. And I'm saying magnitude here because it's absolutely essential. Potential energy of an orbit is negative. Kinetic energy is always positive. And what that means then, to find the total energy, if I add half of the size of the potential energy to my negative potential energy, my total energy is going to be minus 1/2 times the size of our potential energy. The strength of gravity times the mass of an object in orbit times the mass of the object being orbited divided by the radius. So if we take a look at our planet, Earth, orbiting around our star, the sun, or Sol, well, the orbital radius from the center of the sun to the center of Earth is 1.50 times 10 to the 11 meters. The mass of Earth is 5.98 times 10 to the 24 kilograms, and the mass of the Sun is 1.99 times 10 to the 30 kilograms. So if I take my masses, multiply them together, multiply by the universal gravity constant, 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared, and then divide by the radius, 1.50 times 10 to the 11 meters, I get a value of twice this, 5.3 times 10 to the 33 joules for the potential energy with the negative sign, negative potential energy by zero potential energy being infinitely far away. For the total energy, I get half of that value, negative 2.65 times 10 to the 33 joules, and my kinetic energy is going to be the absolute value of that, 2.65 times 10 to the 33 joules. Now, just as a quick extension, we could use energy conservation to figure out how fast we'd have to go to actually escape, to get us up to zero potential energy. Our kinetic energy would have to equal the size of our potential energy. So 1/2 times our mass times our escape speed squared would be the gravity constant times our mass times the mass of the object we're escaping divided by the radius of our distance from where we are right now to the center of the object that we're escaping. So our escape velocity would be the square root of 2 times the gravity constant times the mass of the object we're escaping divided by the radius. So to escape the sun from Earth's orbital radius, we have to be traveling at about 42.1 kilometers per second. And so far, humans have managed to get 5 missions, enough speed to actually escape, so their 5 satellites exiting our solar system as we speak right now. Some have exited. There are a couple of bits of debris from some of those missions that are also going to escape too. But so far, that's it. Thanks for watching.